first lay a background on what do we mean by these high-speed serial technologies. Are there some technologies which are more critical, which are driving the needs for testing, which are driving the challenges in testing? So pick those, understand those technologies, and then from there, talk about what are the ways test and measurement companies have, like ours. I belong to Tektronix, as you mentioned. How are we trying to solve those problems? So let me just move on quickly. A lot of you must be aware of some of these, but the background is important to understand where the challenges come from. Okay, so I will give a brief overview of the high-speed serial technologies like PCIe, USB 4, and DDR5, more with the relevance to their measurement requirements and their specifications, how they are defined. Okay. I think given that we have about 55 minutes approximately now, I would focus about 45 minutes on my presentation, or 45 to 50 minutes, and leave the last 10 minutes for Q&A. And if there's anything further and people want to connect to me, my email ID will be shared, and I can share my phone number as well. OK, now let me just move on quickly to some of the specifications which are critical for us. Let's look at PCIe. Now, I'm sure most of you who are in the high-speed serial domain would be working on or will be working on PCI Express. If not already, very soon you will be there, is what I would expect. The reason being that this has become a high-speed serial technology, choice for people in working on various domains. On the left-hand side, you can see high performance computing is an example. Data centers are an example. Then there is even automotive, for that matter, which is starting to adopt PCI Express. Now, the need is very clear. As the data needs are increasing, you want faster data throughput and faster data transfers from one source to another, from a transmitter to a receiver, I would call it. And as the needs are increasing, people are adapting to higher speed standards like PCI Express. Now, there are when we come to test and measurement, we always look at what are the configurations which are defined in the specifications and what are the test requirements for those specifications. Now, in this case, it is important to know that we differentiate them as PCI Express implementation as either a root complex or as an endpoint. Depending on whether it's a root complex or an endpoint, the test definitions are slightly different, and we'll have to make sure that we cover both of them in our test systems that T&M instrumentation companies are creating. Okay. Now, typical applications, as you would know, are graphics cards, high-speed Ethernet cards. All of these are adapting and utilizing the developments in the PCI Express technology domain. Okay. Now, moving further on this. Why are we talking about PCI Express? What is it that is relevant for people like myself? Okay, over the years, this technology has seen revisions, as they call it, as generations of Gen 1, Gen 2, Gen 3, etc. And each generation has been typically doubling the overall bandwidth or the data transfers that are possible with this technology. So the one which is currently very stable is the PCIe Gen 4, and Gen 5 is in active implementation by many customers and designers, while Gen 6 is already on for early adopters. And the specifications on Gen 7, the early specs are already being defined. Be ready for the next challenges as we move to Gen 7. But key point here is, if you can see, the data rates are as high as 64 giga transfers per second per lane, and which actually transfers to almost 256 gigabytes per second if you're talking of a 16 lane implementation, right? So what does that mean? Each of these incremental or rather doubling of data rates comes with a certain problems as well. What are those problems or what are those challenges? Obviously, as we are going to higher data rates, we will see lower and lower voltage swing between low and high, between 0 and 1. And as designers, you're very keen on making sure that you implement using the highest data rates possible. But as a test and measurement company, we are always worried about the or the voltage swings becoming smaller, because now we have that much lesser window of making sure that we can capture the eye and also give you those eye measurements which indicate the health of the signal transmission. Okay, so what it means is that each generation has added a challenge for the test and measurement industry. Okay. Now let's look at what's the key change when we look at Gen 6, Gen 4, 5, and 6, and some specifications which are relevant from a test and measurement standpoint. Okay. Now, if you see here, the data rate is very straightforward. It is understandable. There's not a problem. But if you look at Gen 6, PCI Gen 6 actually talks about PAM4 instead of NRZ signaling, right? NRZ, instead of NRZ, we are moving to PAM4 signaling. Now, what does that mean? We'll come to that. The other part which you can see is add-in card loss. Okay, so what's the card loss which is defined in Gen 4, Gen 5, and Gen 6? That's one. And the full channel loss again is defined in each of these standards. Now, these are important for us to consider when we are making those measurements, because we are also having to incorporate or emulate the channel losses in our measurement setup so that it's compliant with the standard definitions. The other piece is on equalization. If you see, the reference CTLE characteristics have been defined there, 2 poles, 1, 0, 4 poles, 2, 0. I'm not going to go into equalization in my presentation, but that can be a separate topic altogether on how we take care of these definitions from a test and measurement standpoint. I'll give you a brief intro into this later in the later part of the presentation, but to get deeper in here, we will need much more than a 1-hour session. Okay, and then what about the DFE? What are the characteristics on that? Eye width is a very important parameter here. If you can see that, it says 3.125 picoseconds is the top eye, because we are talking of PAM4 in Gen 6. And eye height is as small as 6 millivolts. Okay, and what about the jitter on the clock? What are the limits? Again, this is a very low, less than or equal to 100 femtoseconds. Now, why are we interested in these parameters, right? Any test and measurement equipment which is introduced, it has its inherent jitter characteristics, inherent noise characteristics. It is imperative that test and measurement equipment are designed to be much better than these jitter specifications which are laid out for these standards. So the challenge on the test and measurement vendors is to bring down their jitter and noise floor characteristics as low as possible, so that these measurements which we offer are reliable and dependable. Okay. Just specific on Gen 6. For Gen 6, what happens is 64 gigatransfers data rate is achieved, and you also have to provide for backward compatibility. So NRZ signaling needs to be also maintained, where the previous generation standards have to be interfaced with, right? The PAM4 signaling actually brings in a lot of complications to the measurement world. And let me just show you what it means. OK, when you look at NRZ, NRZ was a 2-level signaling, right? So it's just one bit is enough for you to define that. Whereas in the case of PAM4, per unit interval, you need to have 2 bits. And it also means that why is PAM4 chosen in this case? Because uh, for half of the bandwidth of NRZ, you can have the same data throughput, right, as NRZ. And what does I mean, it's good in a way, but what are the implications of that? That's what you're seeing on this slide. So four possible transitions versus two, right? Uh, in a given level. And if you really see, the number of transitions possible are 12, and for PAM4, whereas there are only two transitions in NRZ, which is high and low, or low to high and high to low. And eye diagrams per UI also goes up because now we are talking of 4 levels. So 3 eye diagrams have to be captured for measuring one channel, right? And what does that mean? It basically means that you have to capture 3 eye diagrams and also take care that they're all symmetric and aligned, because you're trying to make a measurement on all 3 eyes at the same time. And of course, the clock recovery, right? In all these high-speed standards, clock recovery is important, and most of the measurements or all the measurements are dependent on a good clock recovery. Yeah, and I think we will see more complex measurements as we go ahead with this PAM4 adaptation. More and more technologies will try and look at higher PAM, signaling. Need not be limited to PAM4. You could always go higher as well, PAM8, PAM16, I don't know. So these are things which will happen. But for now, we are interested in solving the challenges of PAM4 while we wait for bigger challenges as we move higher. Okay. And since the eye height and eye width is so small, these are more susceptible to noise as well. So you need to have good techniques to make sure the noise suppression happens and the signal is actually extracted at the other end. Also on the equalization, as we see for Gen 6, there is a second precursor added instead of just having one precursor and one post cursor as it was in the previous standard implementation. And uh, uh, presets are also defined, and they are important for us when we are doing receiver calibration or when we are doing calibration for receiver measurement. Okay. Um, as I mentioned, the equalization topic itself is very complicated, but this example just shows to you that the implementation in the standard is something we have to also consider when we are making test and measurement and providing equipment for you to emulate your hardware, right? So that's about PCI Gen 6. One additional parameter which we find is a complication or a complex measurement is what is called as signal to noise distortion ratio, and as it's called as SNDR. This is also a parameter defined in USB for Gen 2. But basically what it means is that as test and measurement a solution provider, we also have to provide for these kind of measurements in our results. Now, I'll talk about what are the various measurement requirements in terms of board bring up, etc. But it's important to understand the complications or complexities of the new parameters which are introduced by the higher speed technologies. Now, moving over to from PCI Express, just to see the others, how do I say, very important standard. USB is ubiquitous right now with all the data devices and mobiles and all the devices that you use as personal devices. But it had a humble beginning in 1996 with about 12 megabits per second. And now the latest standard we are talking about is about 80 gigabits per second. That's a far cry from where it started. It's not only the data rates which have changed, it's also the type of connectors and cables which are used have also changed. And they bring in the additional complexity of being able to test those cables and for their standards as well. Okay, now what's the key? If you see on the right hand side, the connectors have also changed. And when we talk of test and measurement, we also have to adapt to the various connectors which are defined in the standards to make sure the imperfections in the connectors and implementation by various vendors is all tested, right? Let me move to the next slide. So USB V1, USB 4 V1 talks of 10 gigabits per gigabytes per second and 20 gigabytes per second. Sorry, 10 gigabits per second and 20 gigabits per second. And over two lanes, we're talking of 40 gigabits per second data transfer rates. And important here is that preset calibration is also introduced in USB 4 in version 1. What does that mean? It means that when we are trying to um, uh, provide test equipment, we also have to be aware that this calibration is important and this needs to be measured. Um, Let me see, because we have covered some of the challenges in PCI Gen 4. I'm not Gen 6. I don't want to spend too much time on the specification, but this is a useful thing. So if you see the definitions for loss targets, again, the USB definitions come from USB.org, and the definitions for the loss targets for Gen 2, Gen 3 are all defined here, where a combination of losses in the the host, the cable, as well as device, the max permitted is defined. What does this mean for test and measurement? Or rather, how do you use this in the validations phase? Which means that we should be able to include these loss targets in our measurements and then show you the pass fail as per the standards. Okay, so that's the criticality for us, and that's why we various standard bodies. Okay. And then one quick look at DDR5 6. As you can see, DDR5 is something which is in active implementation now, and electrical and timing specs are already defined for up to 5600, or in fact up to 7200 megabits per second. And 8400 megabits per second. The specs are expected to be available by Q4. And there is a difference between DDR5. Why I put DDR5 and 6 is because up to DDR4, the test requirements were limited to doing a system level test on the DDR standard. But now the specifications are for doing both system level as well as on DRAM level tests, which is both TX and RX measurements, transmit and receive measurements. Okay. And as you move to DDR6, which probably could be a couple of years from now, the data rates are expected to move on to 17.6 gigabits per second, and that will add in more challenges for us. And signaling standard is also being discussed, whether it will be PAM or NRZ. Though NRZ is probably an easier implementation, but when we are looking at the amount of data transfers we are talking about, there's also an equal representation from the PAM4 body as well. People who want PAM4 or any other PAM for that matter for these measurements, for these implementations. On the DDR5, again, just this is not about product, but I just want to tell you that there are two levels of test, as I mentioned. System level test, which is what it traditionally was there up to DDR4. and sorry, and DRAM test, which is now added. So you have to make sure that these two are tested along with the protocol validation as well. So you do an electrical and timing validation and then also protocol validation. A summary of these I'll provide in my overall T&M challenges slide. So now let's look at now I move away from the standards and try and talk about what are the important needs in your design phase. Assume this is post silicon, that is after your design is done and you have got your wafer or your chip or your board ready. So the first thing is about enabling the hardware, which basically will be for power supply related enabling as well as measurements. Could be ripple measurements, could be crosstalk measurements, could be any measurements to make sure your basic signals like clock and others are stable and good. Then there is some basic signal integrity check, which means you would have some specifications which you are going to check for basic eye diagrams where applicable, or the basic jitter specifications for clock, etc. Now, next comes the 5-layer validation. Now, what does a 5-layer validation mean? Now, here you are going to test your device or your board against all the specifications which have been defined by the standards body, right? Now, this is validation. Does it mean compliance? Compliance is slightly different. Validation is where you're trying to make sure your hardware is working as per the specifications. And you might also test for margins. If you're an IP vendor, you would like to provide more margins for your next customer in the next level chain. And so the specification verification becomes very important. What about compliance verification? So as you are expected to be interoperable in the sense that you could make a transmitter portion, somebody else could be making a receiver portion. You want each of them to work together and also give the confidence to your customer who's using your product that they're all well defined. You have to go through a compliance verification or compliance test. And these are compliance test specification which are defined by the standards bodies. And where do we come into the picture? Actually, when the definitions of these standards are happening, there is an equal representation from the test and measurement industry. Companies like Tektronix are also part of these standard bodies, primarily to ensure that we are ensure that we understand the needs for the standard, plus also work back on our end to make sure we have products and solutions available to test the new standards which are coming up. So there are a lot of parallel development which happens between the designers and the test and measurement vendors. For example, for want of any other name, I would like to probably use, let's say Intel was working on the next level PCI Express, or maybe Cadence or Synopsys are working on the next level PCI Express implementation. We have a challenge to make sure that our test equipment is ready to help them make the measurements and also solve their check for their compliance requirements as well as failure validation. Right. In addition, these days, people also want to make sure that not just meet the specifications or compliance, but also provide for check for what margin they have on their design. So that if, for example, if the eye height is defined in the standard as, let's say, 6 millivolts or 6.5 millivolts, you'd like it to be 8 or 10 so that you provide the margin to your end user, right? So even we have to facilitate those kind of testing. Of course, post all this, there is a protocol level testing also, which becomes a need. And in some cases, system level testing also becomes a need. Now, these are the general measurement stages as we see in the development phase for anybody. Now, how do we treat this? Okay. What it means for high-speed serial technologies testing, what does it mean for test and measurement, right? So if you are going to test, so before I get to this, I would say that I normally would say that any test requirement means that you have made a system which has got a transmitter and a receiver with a medium in between or a channel in between or uh, some medium, a transmission channel, wherein the signal travels from the transmitter to the receiver. Now, how do the test and measurements get involved in this phase? If you want to transmit test a receiver, we'll have to emulate a transmitter so that you can do your receiver test, being fully aware that the transmitter is a golden transmitter. It can transmit the signals which are required as per the standard so that the receiver can be validated. Right? What about testing a transmitter? We need to emulate a receiver, right? So what does emulating a receiver means? Which means that we have to provide equipment which behaves just like the receiver in your transmit receive chain, right? So we are actually filling in for the transmitter or the receiver, right? Um, what about the channel in between? The channel in between is also something we need to be able to characterize as well as emulate where required. I'll talk about emulate in in a little detail later, but basically we have to make sure that we are able to take care of the test needs of the transmitter, the receiver, and also able to characterize the channel and the effect of the channel on the signal. So an example is the PCIe transmitter test. If you really look at this, there's a transmitter and there is a receiver on the other end. And in case of PCI Express, there are two specifications which are defined. One is a base specification, the other is a chem specification. The base specification is more at the chip level, I would call it, just to simplify it. And chem specification is more like the IDEN card or the the system level specification, I would call it, or mostly the IDEN card specification. Now, what's the reference that I'm making here? So if you see, if you're trying to do a base level test, you're probably testing at the output of the transmitter in this case, right? If you're trying to do a chem level test, you're actually including all this path, which is your transmit, then the channel, and everything before it enters the receiver or before it is received at the receiver end, right? So the specifications for these two measurements are different, though both are measuring the characteristics of a transmitter output, right? In this case, we'll also have to probably capture the characteristic along the channel at different points to see the integrity of the signal as it is passing through the channel. In some of these standards, there are some test point definitions which are made, which could be for boards or fixture boards which are defined for the standard. Okay. um, Let me just move forward. So let's look at what do we mean by emulated transmitter, right? So it's like saying that I have my receiver to be tested. I need a dependable transmitter to be available, right? So what's a dependable transmitter? Something which is controlled and which has got a very defined output is what you look for. And so what do you need from a transmitter? You need either some sort of signal to be generated out of it, a digital pattern to be generated, also someone who can see that, hey, are there any errors as I transmit the signal and the receiver receives it? Are there some errors along the way? Can I check for the errors? Also, in real world, the signal is not going to transmit and be received at the other end with no loss or no distortion in its characteristics. So the distortion is possible either due to jitter or due to noise. So these are two parameters you should be able to simulate as well. And of course, equalization is something which I talked about, because as you look at high-speed signal transmission and reception, we find that as you transmit the signals, there are intersymbol interference and other jitter components which come into the picture, and you'd like to minimize that impact and see the signal in the right, the true signal at the other end. So there is these characteristics which have to be uh, implemented into the products as well, so that they can also behave like a real transmitter would behave. What are the typical equipment available for this? There is pattern generators. In fact, you can also say signal generators in some case, depending on standard. Arbitrary waveform generators, bit error rate testers, noise generators or noise simulators. Then, of course, margin testers. Actually, margin tester is a concept which was introduced by Tektronix, but I won't be doing a product presentation in today. But if somebody is interested, we can talk about it in a different way, where we provide for how to test for a margin in a fast way. That's on the transmitter emulation. What about receiver emulation? Right? Receiver emulation is basically you should be able to look at the signal which is received from the transmitter, be able to decipher the data which is coming in on the receiver. So that's why we call it a signal capture and analyze or analysis. Capture the eye, measure the eye is something which probably the receiver doesn't have to do. But in your case, you would the equipment is here to make sure that it says, yes, your signal is received properly. And as we look at the eye, we know that a receiver can decipher the signal correctly. A 1 is a 1 and a 0 is a 0. So we need to be able to measure the eye. You also saw the specifications from PCI Express or USB and others. So those specs need to be tested as well. So the equipment should be capable of doing these measurements. Plus, if there is equalization specifications or de-emphasis, emphasis, which is defined, you should be able to adapt that even in the receiver on the instrument side. Jitter tolerance, noise tolerance, all of these are also important, which means you should be able to measure those parameters and be able to eliminate the or compensate for those parameters in some manner. Okay. So what are the typical equipment used here? I think you're all familiar. Oscilloscopes are a very prominent equipment used here. Some people also use spectrum analyzers for certain measurements. Not necessarily in every standard, but in some cases, spectrum analyzers can provide a frequency domain measurement capability. These days, oscilloscopes are also providing for frequency domain measurements. Tektronix has at least been on there. The need is also to measure analog signals along as well as mixed signals. In the sense, there could be digital and analog signals together. This may not be in the case of what you call as compliance test, but if you're really trying to do some debugging, you might want to have a receiver which can duplicate both a digital end as well as an analog end. Separate the jitter components so that you are aware of what are the jitter characteristics. You're preparing yourself. You're preparing your, your designs to make sure that the jitter components which you measure can be eliminated or minimized when your final design is ready. The other thing is on the receiver side, you saw the example of PCI Express channel, right? So if there is a channel and the impact of the channel is such that the signal is distorted at the receiver end, you should be able to kind of eliminate the impact of the channel. This is what we call as de-embedding. And in some cases, because you're not able to physically create a channel, you want to see, hey, if there was a channel, what would the impact on the signal be? Can you help me help and show me the impact on my signal if there is a certain channel introduced? So that's what we call as embedding the effect of a channel. Okay. The last point is also about being able to probe at the right points. which brings us to the other important measurement equipment or measurement component, which is probes. And how are we probing the signal? How are we capturing the signal? Are we using the right methods to get the signal to the receiver? Okay. Let me move forward to the next one. So probing is very critical. In fact, a lot of times people say that the best of the equipment is useless if the probe is not up to the mark or is not matching the characteristic of the generator or the in the case of generator it could be cables, but in the case of analyzer it is predominantly the probes which are getting the signal to the instrument for measurement. So there are probes with characteristics which are well defined. Phase match cables is another important requirement. For a lot of these standards, you cannot access the signals on your boards very easily. So there are test fixtures and breakout boards which are provided by either the standards body or authorized vendors. And also, the other requirement is not just providing the good probes, but also being able to provide the characteristics of the probes for somebody who is trying to do a simulation of impact of probing on their signal. Okay. Um, Let me just move a little further. So how do you characterize? So what do you mean by channel, right? We talked about channel could be a combination of traces on a board, could be connectors, could be cables, could be anything which comes in between once the signal comes out of a transmitter and till it's received at the receiver. So all the interim path can be thought of as a channel, and these channel characteristics can have and any channel will have an impact on the signal, either in terms of amplitude or in terms of phase or both, right? So these characteristics should be something which we can predict or how do I say? Maybe we can simulate those conditions so that we can eliminate the effect of the channels when we are making a measurement at the receiver, right? One of the things which is required from a test and measurement standpoint is be able to characterize the channel well. So S parameters are a very standard method to capture and characterize a channel. A vector network analyzer is something which we required for that. The other option on a time domain, people also are familiar with time domain reflectometry measurements. Both these methods basically are used for characterizing the channels. And if you are using components or cables or even some traces on boards which are predefined, the characteristics of that are typically available from the vendors who supply this, or if they're not available, you can use your VNA or TDR measurement equipment to characterize those channels. The reason why we want to characterize those channels is to be able to look at the signal with the impact of the channel as well as without the impact of the channel. So you can test the signal as it is coming out from the transmitter, and you know where your debugging needs to focus on, right? If you see a closed eye at the receiver, there could be many reasons why the eye is closed. Either the equalization is not properly applied, or your channel is distorting the signal too much, or your transmitter output itself is flawed, right? So you want to make sure that you can eliminate or identify where the impact is coming from. And so you would like to make sure that you can embed and de-embed the channel effects in the measurements. So to do that, you need to have well characterized channel. So that's the reason S parameters and TDR measurements are important. So now, what do we mean by characterization. This is just one example I thought I should use. This is an example from a DDR signal um, analysis. So if you see, um, if you see on the left hand side, we are seeing two eye diagrams. One is a very, I wouldn't say it is a bad eye, but it is definitely not as good as the eye on the right hand side. So the first eye that you're seeing is the eye without equalization applied, right? So this is basically the train we have to on the equipment. These are the steps that we do. DFE on burst signals, train DFE tap and gain values, store and load the trained tap values, and you should be able to view the data I before and after applying DFE, right? This actually gives you the idea of the need for the equalization, as well as how do you say, emulating your receiver, because on the receive side this is all done by the receiver, right? So these exercises are performed on the signal post acquisition, so that if the eye is closed and you're not able to see the eye clearly, you apply the equalization and see if you can open up the eye to make the measurements, right? What about de-embedding? I don't know whether this visible to your eyes here. Uh, so we are basically trying to remove the effects of probe, interposers, and test setup. Okay, and also validate quality of the S parameter files provided. Right. Check the passivity, basically to say that the signals that are received are not see, they don't have a phase mismatch, etc. Virtually, we are trying to move a probe point from some test point to the actual receiver input position or input point. Okay, so the de-embedding helps us in eliminating the effects of any of the channels which come in the picture. Now, what are these files that we apply for this? Typically, these are filter files created from the S parameter, and those filters are in turn applied on the signal which is received, as you're seeing on the left hand side. And then you are able to remap the signal to show you the characteristic as it is after de-embedding. If you have any questions, just hold those questions, because I'm sure we will get enough time to answer those questions at the end of my presentation, which would probably take another 3-4 minutes. Yeah. Um, One example, since we saw an example of DDR, I thought an example of USB would be good to show you what kind of measurements are defined by the standard. The USB org has defined these parameters are important to be measured when you are validating a USB 4 design. Okay, so what are the measurements required? And I'll tell you why these measurements I'm talking about. The standard tests are unit interval, lane to lane skew, transmit SNDR, transmit ISI margins available, transmit swing, pulse, etc. So I won't read out all of them, but you can see that broadly there are standard tests, voltage parameters, jitter tests, equalization effects checked, plus SSE measurements as well. Okay, spread spectrum clocking measurements as well are defined. Okay, now what we do as a test and measurement vendor, whether it's Tektronix or any other vendor, we make test solutions wherein we combine all these tests into a test suite where the users can make the connections as defined. I'll show you one picture of how the connections for a test would happen, and then run the tests in a sequence, all of them, and generate a report, which will be a compliance test report as defined by the standards body. And that compliance test report is your key to make sure that your design is verified and tested. In fact, a lot of these tests happen in Plugfest workshops. and people go with their designs to this plug fest, where companies like Tektronix have their booth, and we have equipment lined up there. People bring their designs, and we run the tests for them and show the results to them to tell them whether they are compliant or they have some parameters which are not so good, some parameters which are good, and so on, right? So these test specifications are important for us because we base our test solutions on these test definitions. This is an example of how a base, I mentioned about PCI Express base and chem specifications. This is how a base test setup would look like. So if you see, there is, if you see that there are certain channel related connections which you can see. There are so many components which come in the way from the oscilloscope to the device under test, and all these are characterized, and the cables and everything else is defined as what can be used for the spec verification, and what are those identified components which you should be using while making these tests, right? The setup is some of the setups can be quite complicated. This is not as complicated as I would uh, think the certain other test specifications lay out as. Then, if you look at um, chem TX specifications, now this introduces much more complexity. You can see there is also on the lower bottom on the right hand side, you can see there is an add-in card placed on a fixture, and then you will find that the cable definitions are there. So if you really have to do characterization and compliance, then you need to make sure all the defined components are available with you before you perform those tests. Because these tests can be really skewed if you have one component out of spec in the whole chain, right? So it's important that you have all the right equipment in place along with the cables and probes and interposers and fixtures which are defined. Okay. Um, then let me see. So that's more like what I wanted to present. I think I'm more or less on time. I wanted to be done at 3:50. But this gives me an opportunity to now open for questions.
Yeah, thank you, Naresh, for a very insightful presentation. Really appreciate. So the floor is open for any questions from the attendees.
If I don't get questions, I will ask questions as well. Maybe just to understand, uh, do you, I mean, is there any, uh, do you guys understand the equalization requirements, whether it's CTLE or DFE or FFE? Any one of you would want to tell how you implement that? Because for us, a lot of effort goes into emulating those things in our equipment, right? Yeah, so that's why I was keen on understanding if anybody has any comments on that.
So I'm sure some of us will be aware with that. I think this is continuous time equalization you are
Linear
talking about.
equalization,
And,
linear,
yeah,
linear
and then
equalization, yeah.
one is digital using FIR and all that DFE goes in the way.
Right,
So yeah. So one question I am having here.
please.
So especially in the context of the data rates which you are talking about. So like what is the way of measuring? Like do you really need those high speed oscilloscope, or like how you are going to measure this high? But because like if we
Mm,
look at the
good.
oscilloscope specification also, so
Hmm.
they are limited up to let's say several gigahertz. So
Hmm.
if I have to characterize it, what is the general approach?
Good question. Good question, because I think I didn't want to bring in any product specifications as I had spoken to Sanjay also. I will not bring any product, but I'll tell you what it is. The scopes are available for beyond 50 gigahertz with almost 200 giga samples sampling rate, right? So oscilloscopes are available for the standards that you need now. Okay, that's
No,
the
no,
first answer.
but
Okay.
you are talking about digital bandwidth, right? So when we capture a signal, the what
Mhm.
we have to worry about is the analog bandwidth, and
Correct.
analog bandwidth is really limited.
No, the analog bandwidths are also adapted already to the needs currently. Even the latest generation PCIe or even Ethernet has got the analog bandwidths covered with the oscilloscope equipments,
I
right?
see.
So I can definitely share those details, Ankesh, and I'll be more than happy to share that with you. But rest assured that, as I mentioned, the standards bodies are defining the tests, and we are parallelly making sure our equipment is also able to help the designers cross their design phase as quickly as they can.
I see. So basically there is directly one-to-one measurement, because I was thinking maybe there is some on-chip solution where you do some processing to reduce the
Mhm.
speed, then you characterize, and then you do post-processing. That kind of thing is not done.
No, no. In these standards, they define that you cannot be doing that post processing in that sense. OK,
I,
the post processing which we do are applying those filters, applying those other things, right? Like the equalization characteristics and so on. But the capture, the absolute capture which happens, that's the signal with the full characteristic which is captured. OK, and typically what you look at an oscilloscope is typically, let's come to the oscilloscope because that's the bigger equipment in these high speed serial standards. One of the things people look at is saying, hey, do we have twice the what do you say? Nyquist rate is one parameter. The second is the rise time characteristics. Basically, we look at the bandwidth of the signal by looking at the rise time of the signal rather than just the frequency component, right? Because how fast the signal rises will also define what's the bandwidth requirement for a scope to capture that. OK, so that parameters are already matching with the equipment available. The sampling rate is one part of it. The bandwidth is a second part of it. The third is the connection, the probe itself, which comes in between, right? So many of these standards don't ask you to use any oscilloscope probes. They actually ask you to use coaxial or SMA, SMP, those cables, so that you're not adding any characteristic from the probing as well as not attenuating the signal any further, right? So, so these are parameters which are relevant for us, Ankesh, because without that, we can't be validating the signals.
sure. Thank you.
Yeah.
Thanks, Sankesh. Any further question?
Sorry, I have one question. My
Please.
understanding, the scope can support us to, I think the scope can support the software, CTRE and the DFE, also include some channel. I'm not sure if we can configure the channel performance by ourselves, also include the CTRE parameter, DFE parameter, such as we don't want to use the reference EQ parameter. We want to configure by ourselves. Can we do it?
Yes, there are. In fact, I have to mention this. We have, for example, Tektronix has one software. We call it as SDLA software. Okay,
Yeah.
which is serial data link analysis software, which is part of this exercise, and that helps you to create those filters based on the parameters that you define.
Okay. Okay. Okay, but as you know, this is the ideal config the parameter. It's different compared with our actual circuit design. From a circuit design, perhaps we face to some power supply limitation. If we amplify something, signal, perhaps we face to some power supply clamp. But for the ideal equalizer, perhaps generate many amplifier. I don't know how to handle it.
So again, let me probably modify my answer. I would say
Uh-huh.
that the emulation, let's call it
Yeah.
emulation. OK,
Yeah.
the emulation is as good as the definition that you can give it to it. Okay.
Okay.
So
okay.
so it's not, it's also about when we say that the measurements are the instruments are doing a lot of measurements, it's also about how the engineer applies it for his or her need. Okay.
Yeah.
And
Yeah.
so the definition is as good as how much you understand about the problem. These are, and most of the people who are doing this debugging and validation are qualified engineers who know what you, for example, you know what you're talking about, right? So you
Yeah, you're
would
right.
like that intelligence is required to be applied when we are using some of these tools. Okay.
Yeah.
Unfortunately,
Okay.
they're not like simple tools to use, but then
Yeah.
the
Okay.
problem is also complex. So you need people with the knowledge of that parameters.
Yeah. 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 I understand. Sometimes we want to know how to configure our internal receiver can meet the requirement. So we want to try something. Yeah. Okay. I understand.
So so my suggestion to you would be, if you can just look at or maybe connect to me, I'll give you some information on what we have as the SDLA. I only for that tool, just to understand how it is implemented and how you can use it for your analysis, right? So
Okay.
that may be a good reading for you. I'm not saying you should use that. At least it gives you an idea of how we do that exercise.
Okay. Okay. Thank you. Thank you.
Thanks for the question.
Yeah, hi Naresh. I have one question. This is Suresh Kumar.
Yes, Suresh.
So, yeah, so I worked on multiple high-speed interfaces and like protocols, DDR and HSIO. But one thing I'm always so when we do measurements actually, so there is a multiple solutions are there. Like we have a keysight solutions with high speed, even though 65 gigahertz max bandwidth of oscilloscopes, and different kind of vendors are also there. So why
Right.
we need to especially we have to pick it from Tektronix. If you see the keysight has a lot of solutions, the compliance, the solutions we have. But of course, we have Tektronix solutions as well as because we have a wide variety of these solutions. So why
Sure.
especially we have to pick the Tektronix? Is there any
Good
specific?
question.
Yeah.
Good question. I would like to give a marketing answer to that, but right now I don't want to do that. But Suresh, which organization
Yeah.
are you in?
So presently in Eindhoven NXP.
Okay,
With
no
same
problem. Let me
Sanjay
just
Sir.
give you a quick answer. Okay, I don't want to
Yeah.
make it a marketing answer, but I'll give you a quick answer.
Yeah, that's
All the
important, right?
vendors,
So
how
yeah,
it's important.
because
It's important.
the engineers has to preference. Okay, we need this equipment when we doing this kind of validation. So then
Right.
based on that, the MT will decide. Okay, we have to purchase which kind of solutions we need, right?
Absolutely.
So
Absolutely. So
yeah,
I will tell you that as far as I'm concerned, by the way, I worked for many years in the other company. Okay. My longer stint has been with that company, right?
okay,
So
okay.
the solutions from both vendors are good. I will not say that they are bad or we are bad, but when it comes to
Okay,
certain specifications, you will have to
okay,
take that call. Okay. Is it,
okay.
it's not about the bare instrument, which actually makes the whole solution. It's
Okay,
about how well it allows you to adapt, how well it allows you to define some, like, the previous question from Zhao was about, can we modify some parameters? So some of those nuances are some things where there are differences between different vendors. Okay. For example, we provide certain flexibility in defining, just like he mentioned about the equalization characteristics. Okay.
okay.
And we can allow you to define certain filters. Some of them are easier. And again, test vendor choice is by engineers is always I wouldn't say flawed. It's always
Mhm.
dependent on past history. They
Okay.
sometimes tend to get stuck there and not look at other options. I always tell people, you
Exactly.
know,
I agree that. I
yeah,
agree that is
we always
seeing
say that you
multiple issues
evaluate,
in kit
you
site. Yeah.
evaluate, and people like us. I
Mhm.
am not directly doing this evaluation, but my colleagues will be more than happy to come and show you what is that difference. Again, this is
Yeah.
not about comparing A and B, so I'm not doing that today. But all I'm saying is it would be good for you to approach us. You have my mail
Yes.
ID.
Yes. Yeah. Yeah.
Approach us saying, hey, this is my need. Can you guys come?
Okay.
Then the decision making is on your end at the end of the day, because there's so
True.
many
True.
technologies, so many variants. A decision is
Yeah.
always at the user end. We try
Yeah.
and help you reach that decision, probably in our favor in most cases. But then the choice is still yours, right?
Yeah. Of course, if I need at least if I meet my requirements, then yeah, of course I
Absolutely.
will go with which are the best ones. Yeah.
People go with best value for money these days. Let me put it that way, because
Yeah. Yeah.
the expense is very high. So people
Yeah.
want
Yeah.
to optimize their expense, at the same time be able to do their job. Now that's where we
Especially if you.
normally say, yeah,
Yeah.
yeah.
you're going higher bandwidth, the more it's more expensive. If you go for
Do you need it
20
is the
gig,
first question. Do you need to go for the higher bandwidth? What is your need? So that's place where the
yeah.
technical team is able to help you. In fact, in many cases, we also help you customers make their measurements first before they choose the equipment.
I want to mention one more point actually. So recently, what I heard from so our team actually AMSIP from Eindhoven team. So what I heard, so they want to start with a new cluster actually with the high speed SerDes actually. So might be because if they start designing about high speed SerDes and all, so definitely they need a validation team as well as I hope.
Absolutely.
So we need a more equipments on the like characterization of high-speed devices. So might be
I would definitely like to
maybe
talk to you, Suresh. Please provide,
sure.
give me a message and I will connect to you. But
Yeah.
here is a comment for everyone else listening, because I don't want to make it between you and I, is that
Yeah.
there are many choices for you in the industry. I told you about what are the general test and measurement approaches for solving these problems. We have dedicated teams of engineers and application team who will come and explain to you. Yeah.
Okay. Yeah.
Okay.
Let's make
So
that's
that's a
makes sense.
general
Yeah,
answer.
that's
I don't
nice
want,
actually.
I mean, I had my agreement with Sanjay, I'll not talk product.
Okay.
Yeah. Thank you. Thank you very much. Really appreciate Naresh.
Appreciate the
Yeah.
question, Suresh, still. Yeah.
Yeah,
Yeah.
indeed. Okay, I think we
Thank you,
are
Naresh.
3 minutes over time. So I think we will stop here. And once again, Naresh, thank you very much for such an insightful talk. It has been really pleasure listening this.
And
And I
thanks
would
for the
say,
audience also being around for
yeah, indeed,
1 hour. Okay.
indeed. And this session has been recorded, and we will be sharing the details soon on the IEEE SSCS daily chapter. And on my LinkedIn as well, I will post. So guys can you feel free to circulate that to other colleagues.
Thank you so
So
much,
thank you very
Sanjay.
much, Naresh.
Thanks for
Yeah,
Ankesh. Thank you so much.
Yeah,
thank
thanks.
you.
And in fact, I would like to add that whenever you are visiting Delhi, just let us know. We would like
Yeah,
to
sure.
have you in person, and
Soon.
maybe we can ask you to speak on some other topic and
Definitely. Definitely.
share the
Definitely.
knowledge.
Soon I have a plan to visit Delhi,
Yeah,
probably in
thank
July
you.
sometime.
Yeah,
So we
yeah,
will meet up. Yeah.
sure.
Thanks to
Thank you.
everyone else who's participating. Thank you so
Yeah,
much. Hope it
thank you
was
very
Thank
useful.
much.
you.
Yeah.
Yeah, bye
Thank you,
Thank
bye.
you.
Sanjay. Thank you.
Bye
Bye.
bye.
Thank you,
Yeah,
Naresh.
bye bye.
Yeah. Bye bye.
Bye.
Bye, Sanjay.